I have a few examples of trig equations to solve here, and depending on which homework problem you're in, you might see any number of these. These all have something special about them, which is extraneous solutions. Those are solutions that are actually not possible for various reasons, and we'll go over each of those in turn. And I'm going to start off with this guy up top here, this 3 secant equation. And solving equations is a lot like, solving trig equations is a lot like any other equation. You want to factor it generally. That's a very good tool we have. So the first thing I'm going to do is rewrite this as 0 on one side equals tangent squared omega, secant omega. And here's that 3 secant, which I've subtracted over to the right side so I can get 0 on the left. And now we think, well, how can we factor this thing? GCF should always be one of the first tools you have. So that we get 0 equals, what do I factor out as my greatest common factor? That's a secant. See, both of these terms have a secant omega. So secant omega times tangent squared minus 3. Sorry, I'm getting a little casual here. Tangent squared omega minus 3. So now we solve each of these separately. And we get secant omega equals 0. And we get tangent squared omega equals 3, which leads us to tangent of omega equals plus or minus, don't forget that plus or minus square root of 3. And now we have a bunch of angles that come out of this. So where does secant equal 0? Well, I don't have my secants memorized. So actually, let's back up a little bit and say secant equals 0. That means cosine equals 1 divided by 0. Remember, cosine is the reciprocal of secant. So if you have a secant number, you just flip it over in a fraction, and you get your cosine number. Well, what's 1 over 0? That's DNE. It doesn't exist. It's like infinity or something. So we actually get nothing from that guy. Secant is a nonsense solution. All we have left is this tangent one. Tangent squared equals plus or minus radical 3. If you remember a unit circle, remember the tangents at radical 3's are up here. They're those high points, very high up on the edge. And plus or minus, the minus signs are in quadrants 2 and 4. So these are our angles that we're looking at here on our unit circle. Okay, that looks like pi over 3, 2 pi over 3, etc. Okay, so omega equals pi over 3 in quadrant 1, 2 pi over 3 in quadrant 2, 4 pi over 3 in quadrant 3, and 5 pi over 3 in quadrant 4. And from the secant portion of this equation, there's nothing. So that's it. Now, next equation. We need a little room here. You go down there. 3 cosine equals negative 4 sine squared. Again, I want 0 on one side. Okay, but in this case, I'm going to add 4 sine squared cosine, because I want my quadratic term, that's the most complicated term, I want that to be positive. Just makes things easier. So on the left, I'm going to have 4 sine squared omega times cosine omega plus 3 cosine omega equals 0. Well, now I factor out my GCF, that's cosine of omega, and what's left on the inside? That's 4 sine squared plus 3, it looks like. Okay, 4 sine squared plus 3. And now we solve each of these separately. So on the one hand, I have cosine omega equals 0. On the other, I have, let's see, did I do this right? Yep, this looks good. I have sine squared of omega equals negative 3/4. Those are my two solutions that I get here. And the first one, pretty easy. That just means omega equals pi over 2 and 3 pi over 2. Those are the angles on the unit circle that lead to a cosine of 0. That's the x-coordinate. Okay, if I was talking about this unit circle up here, these are the points I'm talking about. Okay, pi over 2 and 3 pi over 2 where the x-coordinate is 0. Now, sine squared is no problem. You just square root each side. So I get sine omega equals the square root, plus or minus the square root, remember, of negative 3/4. And now we've got a problem. You can't square root a negative. You get imaginary things. So don't worry, we are not getting into imaginary trigonometry. All we're going to do is just say d and e. Okay, so here's your full solution. Pi over 2 and 3 pi over 2. Now, both of these extraneous examples came about because we had something that we weren't allowed to do, either 1 divided by 0 or square root of a negative. Those are one type of extraneous solutions that you'll run into. Here's another type. This is the last equation. Negative 2 cotangent equals blah, 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 blah. Now I'm going to take the more complicated one, keep that positive, which means I want to add plus 2 cotangent to each side. So I can get 0 by itself. 0 equals 2 times the cotangent times the cosine plus 2 cotangent. And now we look for a GCF, and it looks like that is this 2 cotangent. Okay, so it's going to be 2 times the cotangent of omega times, well, what's left behind? Careful here. This is where a lot of people make mistakes on simple greatest common factoring. I have a cosine left behind from this guy, and then I have a plus 1 left behind on the right, okay? Because when you divide 2 cotangent by 2 cotangent, you just get 1. Okay, so there's my factoring done. And now what's left is to solve this from this guy right here. I get 2 cotangent of omega equals 0. Well, that's no problem. If you remember what cotangent looks like, where's the cotangent equal to 0? It's on these points right here. Okay, that's cotangent equal to 0. So, what do we get there? That's going to be omega equals, looks like pi over 2 and 3 pi over 2. And now the second part of this equation, which I'll make in purple, this guy says cosine of omega equals -1. Well, where is that true? That's going to be over here. The x-coordinate is -1. So that's omega equals pi. And at first, I mean, everything looks great, right? I've got 3 angles. I'm ready to say my solution is pi over 2, pi, and 3 pi over 2, except there's a problem. We have domain restrictions that we have not spent a lot of time talking about yet. But think about the domain restrictions here. I'll use running out of colors. When you have domain restrictions, you have to look at each trig function in turn. Now, does cosine have any domain restrictions? No. There are no domain restrictions. In other words, any angle that you plug into cosine is going to be just fine. But cotangent, on the other hand, cotangent has some very real domain restrictions. You cannot have angles of 0 or pi. Okay? I'm talking about these things right here. Cotangent blows up at these points. So those are very bad things. Those are things to avoid, meaning this guy right here, extraneous. If we plug in pi into that original equation, you're going to see it blow up. Cotangent of pi is infinity. So this is our solution set. Pi over 2 and 3 pi over 2. We had to rule out one of the solutions because of the trig function that has a domain restriction.